For our next discussion of light, we want to talk about where does the light come from. So to do that, we have to realize there's lots of different ways of making light. And in astronomy, lots of different kinds of things make light, and they make light in different ways. The way a star makes light is not necessarily the way a nebula makes light, which is not how light's made, near a black hole, etc. Simplest way of making light is to make something hot. Okay, this is how fire works. It makes things hot. And what happens is the electrons, which make up materials, atoms are made up of electrons and protons and neutrons. So as things are moving around, then what happens is that the electrons are bouncing around. That's changing electric and magnetic fields. When that happens, then it makes light. And so the faster the molecules move, the higher the frequency and the shorter wavelength of light. Okay, so red light's long wavelength and blue light short wavelengths. So an object that's bluish, that's glowing blue, like a blue flame, is going to be hotter than one that's glowing reddish. Okay, so we call this thermal radiation, or sometimes blackbody radiation, because the mathematics that describes it works both for absorbing and emitting light. And so a blackbody, or a continuous spectrum. So if I were to look at light, it's all different colors of light. The peak, so if I were to make, in other words, I would have all the different colors of light, red, orange, yellow, green, blue, indigo, violet, but one color is brighter than the rest. And so the brightest wavelength is given by Wien's law, and that is lambda max is 0.0029 over t. If I do algebra, I can write it like that. So let me explain what this means. In the Wien's equation, there's a T for temperature. And so the question is, what kind of temperature do you measure? In the United States, we often use Fahrenheit temperature. In many other countries and in most of the sciences, we use Celsius temperature. It turns out neither one of those is really the right temperature. What we want is zero temperature to be absolute zero. Remember, temperature is a measure of the kinetic energy of the molecule, so you want zero to be absolutely zero, so there's no motion of the molecules, so zero temperature. And the scale that does that is what we call the Kelvin scale, in which 0 Kelvin is the absolute zero. On the Kelvin scale, water freezes at 273 Kelvin, water boils at 373 Kelvin. So let's do an example here. So we have an object right here, like a human being. So a human being is about 310 Kelvin. And so what you're giving off light because you're not absolute zero. So what wavelength do you give off most? Well, that's 0.0029 divided by 310. So 0.0029 divided by 310 comes out to be 9.35 times 10 to the minus 6 meters. That's the same as 9,350 nanometers. Remember, you only see 400 to 700 nanometers, way longer than visual light. And so that means that it's going to be infrared. The sun, on the other hand, is 5,800 Kelvin. So what wavelength does the sun give off most intently? 0.0029 divided by 5,800. So if you take 0.0029 divided by 5,800, what you come up with is 5 times 10 to the minus 7 meters. That's exactly the same as 500 nanometers. Now, what's the range of colors that you see? 400 to 700. Now, the way your eye works, you actually see the same number of colors between 400 and 500 as you do between 500 and 700. So 500 nanometers turns out to be right in the middle of your visual acuity. In other words, your eyes are perfectly made for a creature using sunlight to see. Okay. So that's a very useful thing. That's useful. I mean, you can see. I mean, we'll presume that Klingons or Vulcans, because they grow up around different stars that maybe are different temperature, see a different range of colors than humans do. Okay. Now we can run this thing backwards, and we can say, "Hey, I'm looking at a star, and the star I can measure the the brightness of the star. I can measure the peak wavelength. So the most intense color is going to be in that particular star is going to be 411 nanometers. Okay, and I want to know what temperature of the star. So the temperature is going to be 0.0029 divided by the peak wavelength. So in this case, it's 0.0029 divided by 411 nanometers. Well, this is actually meters, so we have to convert nanometers to meters. And nano means 10 to the minus 9. So it'd be 411 times 10 to the minus 9. Okay, so if I divide this out, 0.0029 divided by 411 10 to the minus 9, okay, that comes out to be a temperature of 7,056, or we just write 7,060 Kelvin. Okay. Now, this is actually not just done in astronomy. This is actually used industrially. For example, when you're making steel. You want to make steel, you have to cook the materials at a certain temperature. Well, it's molten. You can't just stick a thermometer in it to measure what temperature it is because it'll melt your thermometer. So what you do is you look and see what color it's giving off. And the color that's being given off is related to the wavelength. So you just adjust the temperature into the wavelength is what you need it to be that particular temperature. Okay. Similar sort of thing to these non-contact thermometers. You point a thermometer at something and you don't even touch it. You just point the thermometer at it, tells you what temperature it is. And what it's doing is it's measuring that wavelength of light that's coming off and using that to figure out the temperature. So this is Blackbody radiation. Red turns out to be longer wavelength. The longer the wavelength, the cooler it is. And so red, and then orange, yellow, blue is going to be the hot things. And so now the interesting thing is that an object that's 3,000 Kelvin is going to peak in the infrared, but you can still see it because it's giving off some longer and some shorter than the peak. And it's giving off more red than blue, so this object would actually look reddish to you. Something about 6,000 Kelvin is giving off all different colors of visual light and would look almost white to you. Something that's 12,000 Kelvin is peaking in the ultraviolet, so giving off more UV light than anything. Think about it like arc welding. It gives off more ultraviolet light than visual light, but you can actually get a sunburn from arc welding. But it's giving off more blue light than it is red light, so it's going to look bluish to you. Okay, and so you are seeing visual light, but you're giving off even more invisible light. And so this is an example here of what we call blackbody radiation. The sun is a blackbody. So the sun peaks in the visual part of the spectrum up here. It gives off ultraviolet light. It gives off infrared light. Infrared light, that you can feel that. Go outside, it's warming you. You don't see the light that's warming you, but it's warming you. That's infrared light. Okay. The dashed line is showing what a perfect black body would look like. The jagged little sort of line in here is really what the sun's doing. It's slightly different than the perfect black body, and that's because there are other factors going on in there. But this is basically thermal radiation. The brightness is given by the Stefan-Boltzmann Law. Luminosity, this is the power output, the energy per second. It's related to the temperature in Kelvin to the fourth power. So that means if you double the temperature, it's going to be 16 times brighter. It's related to the area. So the bigger it is, the brighter it's going to be. And then this thing that looks like an O with a tail on it, That's a constant, we call the Stefan-Boltzmann constant. So that equation right there is something that we can use. We're not going to do it in this class, but you ought to know it is usable to figure out how much power is coming out. Or if you know the power coming out, then you can work backwards to figure out temperature. This is how some of these non-contact thermometers. Okay, so different stars have different absolute magnitudes. Okay, why? Well, if they're hotter, they're going to be brighter. Stefan-Boltzmann Law. If they're bigger, the bigger area means brighter. Stefan-Boltzmann Law. Okay, and so if they're cooler, they're going to be dimmer. If they're smaller, they're going to be dimmer. So now we can start working backwards and figure out from peak wavelength what color is most intense. That would tell you the temperature, okay? And then we can figure out the size using the brightness. So the question is, how does all this blackbody radiation matter to us? Well, here we have a picture of Pluto. No spacecraft has ever landed on Pluto, but we know the temperature of Pluto because we can look at the light being emitted by this world and figure out the temperature of the surface just by looking at the light that's coming from it. So this is how you actually measure temperatures. And of course, here with the virus pandemic, they have these temperature measuring things here, thermometers. They just point at your forehead and it measures the temperature. Well, how does it do that? Well, it's measuring the light being emitted, the infrared light given off by your body. And because different wavelengths of light are given off most intently at different temperatures, it just measures what temperature, or rather what wavelength is most intense, and that tells you what temperature you are.